Hey, my name is Eugene, and I'm here with Near. And today we'll try something new. We'll go through one of our contracts in Rust, and we will review how it's all done. And this is the first session, so let me introduce myself. So I'm Eugene. I work at Near. I work on runtime and contracts. And um, let's go next. With me is Mike.
Hey, I'm Mike. I'm a DevX engineer. I've got some Rust experience, but these contracts we're looking at today are going to be new for me, so it's exciting.
I'm Chad, in the same position as Mike, DevX engineer. This contract is new to me. Less Rust experience even than Mike, but like some familiarity. So, Josh, who are you?
I am Josh. I am also a DevX engineer, and my Rust experience is even lower than these individuals. So I'm really looking forward to learning more.
My name's Sharif. I work on education in Near. I can spell Rust confidently. Looking forward to it.
All right, let's start. Let me present my screen. Today we're gonna discuss a voting contract, and this is the contract that was used by mainnet to move from phase 1 to phase 2. So validators had to vote to enable transfers, which essentially made the network fully decentralized. Okay, so this is C-Line. I'm using it as one of the greatest tools to work on Rust. And this ID, so on the left, you can see a repo for core contracts. This is open sourced on GitHub on our page. And there are a bunch of contracts, and one of them is voting. So let me first go through a quick structure of how this all works. So on Rust, you have src and lib. Lib is a main file. It's a library because we're not really compiling a binary, but we're compiling a library into WebAssembly. There is a cargo toml. This is the way to describe dependencies. So we're saying we're going to build a voting contract, and we use NEARSDK version 2.0.0. And there's a bunch of flags that we use to tell how to compile this release build. So there are a bunch of optimizations that improves the size of the code. Then we say there's no debug info in the release, and also panic is aborting. This is important for WebAssembly. And finally, we have overflow checks equals true. This means when integer overflow happens, something like you can subscribe, or you can subtract a number. So let's say you subtract 2 from 1, and this goes to negative. And if your integer is unsigned, this will make it panic at this operation. So on C++, it usually silently rolls over. So on Rust, you can enable a flag that will make it panic on any overflow, or if you exceed the limit of the integer in either direction. So if you go beyond U32, this will also panic. And when you develop contracts for any smart contract platform, usually overflows, silent overflows are not intended behavior and can lead to abuse. So ideally, your contract will panic and you'll just handle it. So this is just for safety. Then we have other files, and we'll go there later. But first, let's start with the main contract. So this is a single file, and it is fairly simple. At the same time, it has some interesting stuff. So the way contracts are done at Near Protocol in Rust is we have a main structure. So in this case, we're using a structure called voting contract. Structure is similar to class in other languages. and we have a few macroses here. So NEARBindgen is a macros from NEARSDK that turns the structure into something that we use for contracts. And I'll go later into details. And Borst deserialize and serialize are two macroses that allows this structure and all fields in it to be serialized to our binary format called Porsche and deserialize it. And this is needed to be able to store this entire contract into a state. So the way contracts work is they have some persistent state from which they can read information on every invocation of the contract. And then they have a local memory, which is only available when a contract started. So let's say it's probably going to be better explained later. So we have a structure, and then in Rust, you have implementation of the structure. Implementation of the structure is basically methods of the class. So one of the methods is new. This is a constructor. It doesn't take any arguments for this particular contract, and it returns self. Self is equivalent of a voting contract. Basically, it's saying that it constructs a new instance of this class. We have a decorator macro called init, and this init allows us to initialize a state of the contract without having a previous state. The way how contracts usually deployed on Near protocol is you deploy the code of the contract. Essentially, you deployed a class, and then you need to initialize an instance by calling a constructor. This will write a state, in our case, this particular structure, into a persistent storage of the contract. So it will be available every time you call this contract. Does it make sense so far? Okay.
So far, so good. So far, so good. There's a couple of ideas that you're talking about that are a little bit new, but I expect watching the video again would help.
Okay. So let's go through the constructor first. So when you first initialize the contract, the voting contract, it doesn't take any arguments because, well, it doesn't need to know anything because it will only rely on the current context of the blockchain. And this context comes from a module called env, which is short for environment, from NEARSDK. This is where we'll need information down the line, and we'll use arguments that other contracts or users call this contract. So there's two things happening at the constructor. First, you check that the state doesn't exist. It means the contract is not yet initialized. So this macro allows for the contract to be called multiple times. So it doesn't check if the existing state already there. It allows to do this. We are working to add another macro, which is we call init once, that will allow only to initialize the contract once, and it will do this check automatically. So assert is similar to unit test. It just verifies that the given expression is true. And if it's not true, then it throws a panic, which stops the current function call and sends this message as an error. So it's saying if the state doesn't exist, or if the state already exists, basically inverse of this, then the contract was already initialized. And we cannot initialize this again. So if we didn't have this, then we would be able to override whatever was there with the new state. Then
Question.
we have, yes.
Does state exists work together with init? Is that where it comes from? Like what state is it checking?
No, so state exist is actually comes from NEAR protocol. And this is the internals, how it works. So we probably need to look at how NEARSDK in Rust works to better explain. So every time not a constructor is called, so let's say this is a method, it takes the argument mutable self. And by using this decorator near bindgen, it creates a specific code from this contract that does a bunch of operations before getting into the execution. And one of them is if you take mutable self or self, it first tries to deserialize the current state. The way it works is on a low-level API, we have a state key. So this is the key for which we store data of main structure. So let's say in a constructor, we constructed this state. Basically, this is a return in Rust. If the last value, we return this new structure, which we initialized the way we want it. And then this structure, by this macro getting serialized to a binary format, Borsch, and getting written into this persistent storage under a key state, and the value going to be the current value of this structure. So next time a method is called like this, it first will read the binary part out of storage, deserialize it, and create this structure. So, and then only after this part will start getting executed. So this is part that comes from NEARSDK. It's basically a wrapper around. All it does, it checks if the given storage has this particular, if the storage has this particular key, and if it has a key, then it knows that the state already exists.
Okay. I was thinking that maybe the contract itself, the binary of the contract, was being stored in the same location in some database with the state. So that was part of my confusion. The other part is, what does init actually do?
So init allows you to, at the end of so it expects that you return a new class or a new instance, and it will write it to the storage. So this is what it does. Basically just saying that I don't expect any arguments, but you will return me a new state that I will write into the storage. So
it's indifferent as to how many arguments, to clarify, right? Like you could pass arguments. Okay.
Yes. Okay. So we can also have a default on the contract And we don't want our contract to be initialized with the default argument without calling initialization. So we say if a default method is called, so this happens when the state doesn't exist, so it was not initialized, then this method is called default. So we don't want this to happen, so we're saying it should be initialized first. So it basically just panics with an error.
Usually, isn't default called automatically when you call any other method on the interface? That's why you have to kind of override it with this panic.
So yes, NEARSDK, it basically tries to first read the state from the storage, from the state key, and if it doesn't exist, then it will call default. But if it exists, then it's not going to call default.
Gotcha.
Cool. So let's go to the first method and see what we have. So let me just see the interface first of the contract. So we have a few methods, and Rust has a decorator of pub, which means visibility is public, and if there is no visibility, it means that it's private. So near bunch decorator only turns public methods into the methods that you can call on the contract, which means check result method is not exposed to the contract. It cannot be called by someone else. All the rest of these methods can be called by anyone, essentially. So
and just to double check, in Rust syntax, the pub modifier could be on the implementation. All the methods could be non-pub, but the implementation's pub, and then they would all be part of the interface.
I'm not sure about this. I think implementation doesn't have a, well, maybe
okay.
I
don't know either. That's why I was just checking. I think I saw that before. Now.
Okay. I don't think it's true, but I don't want to argue because I'm not sure about this. So one more important thing about NEARSDK is a difference in arguments that you pass. So if you pass argument mute state, it means the method will be allowed to modify the state. We call this type of methods regular function calls, so they can only come through a transaction. And in contrast, there's a without mute self. So the state of this structure will be immutable. It basically a read-only state. You cannot modify it. And this type of methods can be called using view call. And they are not going to modify the state. And
so that's a quick way to tell if it's a view method or a change method in Rust. Is just if it is mutable, you can assume it's a change method.
Right. It can be called as a change method, basically. And I think if you don't have mute self, then it will not write a state at the end. I'm not sure we enforce this as a view method only on NEARSDK. You may want to check this on the next call. But the important part is we should treat them as non-changeable methods. So they are not modifying the state. And usually, usually they intended to be view methods versus mute intended to be change methods. So before we dive into any particular method, let's look into this one. It has an argument in addition to state. So by default, NearBungeon expects methods to be passed, or arguments to be passed as JSON. So default deserializer of arguments JSON. So this piece expects a method to be called with something like the following. So method name vote, and argument's going to be a JSON in format of isVote, for example, true. So this is the arguments, the raw arguments that the method expects. And this is important because you cannot pass arguments using positional call into a contract. But internally, within this implementation, we can call vote with positional arguments. And within unit tests, we can also use positional arguments.
You can use either or.
No, so basically, if you within Rust, same Rust, not calling the WebAssembly binary, before NEAR-binding does its magic to turn it into a contract, then you should use positional arguments. But if you calling it either from simulation tests or from like on a blockchain actually, then you are already calling a precompiled WebAssembly library binary contract, and it will expect it in JSON format. So the raw WebAssembly doesn't know any type inputs, and we parse input completely different. Probably it makes sense next time to go through expanded macro. I don't want to go on this call, but we can do basically run macro expansion on the compiler to see what's the raw code is generated for every method, and it will be easier to see what's happening behind the scenes before we actually get to execution of the body of the method. Okay, and finally, return arguments. So this view call returns an option of wrap timestamp. So the return types after NEAR-binding contract macro expansion are also JSON. So this type is a specific custom type, which is U64. So this is coming from NEARSDK JSON types, and it is a structure. That's probably too much Rust. It's a structure that has a raw U64 type, but when JSON deserialization is called on it, or serialization, it turns it into a string. The reason for this is JSON standard doesn't support all U64 types, like not full range. It only comes from, I think the limit is something like 2 in the power of 53, because JavaScript originally had this limitation on numbers. And JSON standard, the default JSON standard that comes from frontend, will not serialize large U64 numbers into a proper number. So instead, we wrap 64 integers. U64 is unsigned 64 bits integer, and U128 integer into strings. So that method will return you a JSON, something like this, which is basically a string if where the actual number is like 1,000. Or if it doesn't exist, the result doesn't exist, then it will return you null. Okay, so this is high level of NEARSDK. And we can now go into one of the methods. And probably the main method how we get into this contract is a voting call. So when you're an active validator, so you have an account with at least one seat in NEAR protocol, so you have a pretty large stake to hold to have stake to be an active validator, then you can, before phase 2, you can call this method in order to cast your vote. So if isVote is true, it means you want to vote for phase 2. If you said isVote is false, it means you're withdrawing your vote. So let's say you first casted your vote and then you want to cancel it for some reason. So for example, you feel you didn't know something and you want to retrieve it. So let's see how it works. So this is the change method, and it automatically gets an argument deserialized by near binding. Even so, as we discussed before, it was expecting JSON. Internally, it's just a Boolean variable that you can use normally in Rust. And the method is like this. So it's nothing about how the state has changed or actions you did. So you don't need to manually save the state. It will be automatically saved if the method completes. So first thing it does, it's called ping. Ping, we'll go to this method later, but it does update the internal state by checking if the epoch has changed and who's the active validator to update the data. Then it checks if we already reached a result. In our case, I guess we need to first, no, it's fine. So result is a field that's saying if we already reached 2/3 of the validator, then it's just a timestamp at which phase 2 started. And this is a timestamp in nanoseconds because this is how we expose timestamp to within a context. Option means it either exists or doesn't exist. So if it exists, then it's given timestamp. So it means voting already happened and we reached the phase 2 at a given timestamp in nanoseconds. If it's none, so it doesn't exist, it means the voting was not reached. So we check that if we already reached a vote, if you reach phase 2, then we don't need to do anything. Your vote doesn't matter because it's already phase 2 and the timestamp already there. Then
And for like Rust folks who are, or people who are not familiar with Rust, this whole option sum is some none thing is not like a NEARSDK RS thing. That's just like a straight up Rust thing, right?
Yes. So it's similar how JavaScript has 3 types for Boolean, or maybe more, but it can be true, false, and null. So null is the variable doesn't exist. So similar
A lot of
here.
languages have null, but
Yeah.
it's worth saying that Rust does not have null. Instead, it has option types, which can return some value or none. And you have to explicitly deal with it or it yells at you. So, but when it gets encoded for the outside world, it is getting like converted to JSON, for example, it is getting stored, sent as null. I think that's what it is.
Mm-hmm. Cool. So next is the query the context of NEARSDK, and we check who called us. So there's 3 types of accounts that are available from context. One of them is predecessor. This is the account ID of immediate predecessor of who called vote. So Near is a synchronous environment, and you can have a chain of cross-contract calls. So let's say Alice calls Bob contract, Bob's calls Cheryl's contract, and in this case, predecessor is going to be Bob. If we are Charles, then predecessor will be immediate account who called us. In this case, in this example, it was Bob. In contrast, there are also signer account ID. This is the account who signed the original transaction. In my example, let's say it was Alice who called contract Bob, and then Bob called Charles. So signer account ID will be Alice, and current account ID is the account of the contract. So in this case, it's going to be Charles, the account of that holds the contract. So on Near, the contract always belongs to some account on which it stores state and has balance and has code deployed. For security reasons, it's very important to always rely not on the signer of the transaction, but on the immediate predecessor. Because let's say Bob is a malicious contract, and if you would rely on the signer, that Bob can call some token transfer contract and withdraw a balance from Alice to themselves or their owner instead of by acting on Alice's behalf. So if Bob would try to do this, then the token contract will get the predecessor, who is Bob. So contract Bob can only spend balance of their own. So it has some limitations, but this guarantees you that if you call in some contract, this contract cannot really spend your cannot really act on your behalf except on itself. Does it make sense?
Yeah. Awesome.
Cool. So next thing we do is check the argument that was passed. So if it is the vote, then it means we want to add this our stake from the caller to set of active validators who voted for phase 2. So otherwise, the value is 0. It means we want to set our stake to 0. So we call a special method on the environment, which is calls a host function on Near protocol runtime to get the active stake from the current epoch of a given account ID. It will return for a given validator how much stake they have. And this will be done immediately. So this is a synchronous call. We verify that your stake is 0 or above 0 to make sure that we don't pollute state with non-active validators. So this way we can limit how many validators can get into our state. So because we only have 100 seats when this contract was used, it means you can limit the number of validators in the state of this contract to 100. So basically, if a assert triggers in terms of stake is 0, then we throw a panic, and everything we did before this, all changes to the state, will be rolled back to the beginning of the function call, only for this contract. So in this case, again, coming to example of Alice, Bob, Charles, only state of Charles going to be reverted, but state of Bob is not, because of asynchronous environment. Next, we check if we already voted before. If we did, then we just remove. So votes is a hash map. Hash map is in-memory map. It means every time it's serialized or deserialized, all values has to be serialized into one piece and then deserialized back.
Why did you? I think the hash map is interesting. I was just recently talking about this with Mike, actually, and maybe Josh was on that call too. But in general, we give the advice to people that, like, most of the time you want to avoid Hashmap and use a collection from NEARSDK instead.
Yes.
And I'm curious why, what makes this a better case for Hashmap?
Good point. So Hashmap, as I said, whenever we call a method on this contract, it will deserialize all fields of the hash map. So all 100 potential accounts will be deserialized at once. But it will do this into a single storage read instead of 100 storage reads. So this is that even so the overall size of this is large, because each account can be up to 64 characters and balance is 16 bytes. The overall size of this is not as large. So it's 100 times 80. So it's like 8 kilobytes. But we need it in pink. In pink, we have to iterate on every single vote in order to update the stake of the validator. And if we would have to iterate on every single key from a persistent collection, for example, an ordered map, then we will have to do something in order of 100 reads. And in this case, we actually need to override them, which means we need 100 writes. And 100 reads is much more expensive than one-time bulk read of 100 accounts. Because we know that that structure is limited to 100, we don't need to introduce pagination that you might need to do with a persistent map if you would want to iterate. And this is because the trie was stored in the storage is kept as a trie, and this makes it expensive to do a lot of reads. So in this case, it was beneficial to have one map that you will be able to iterate. So the guideline here would be, if you need to iterate on every single key, you probably want to have a hash map or a vector.
But it's also
But-
that you also know that it's bounded, that there won't be more than 100
Correct.
keys.
Right. Otherwise,
And
you
that,
can like,
in this case, that's specifically because there's not going to be more than 100 validators for now.
yes,
Is that correct?
correct.
And
Yes.
if near were fully sharded, then like this will need to be modified potentially with a
Potentially.
persistent map. One of the
Either
nearest keys
persistent map,
collections.
or maybe you can do something like a sharded map. We don't have it right now, not or like bulk map. So it will be a persistent map of like bulk objects, because you still need to iterate on all of them. Maybe you can like split your accounts into 20 buckets, and then every bucket will be a vector, but you will store them separately into persistent map. So when you need to iterate, you only need to read 20 keys, or you introduce some pagination for ping.
Am I correct in saying, I mean, that was a really good explanation. Thanks. Am I correct in saying that like this is kind of min-maxing in the sense that even if you used a near persistent collection instead of a hash map, it's not like it would be crazy expensive, right? But this is just, it's just like better, but like, yeah, I guess that's my question.
Right, so currently our storage is probably one of the most expensive operations that you will usually face by default. And if you do like overwriting of them, then potentially it will be more expensive than a hash map, and that's why we picked a hash map right now. But it's not like dramatically worse. But to be safe, we can pretty much estimate that 100 fits into our current gas limits, and it makes it a good choice for this particular contract.
Cool.
So I think we have like 10 minutes that we want to spend more on this, and let's try to finish some of this. So what happens here is we basically remove the old stake. This is just a safety check, and it's an invariant, as it's saying here, which means it's unlikely to trigger in a real environment. So it verifies that the current stake is less than the total stake. Then we subtract the old stake and introduce a new stake. While I would argue that order of this would be better to be first subtracting the old stake and then introducing a new stake in order to avoid overflows. Even so, with our limit on total supply, it's not possible to overflow, but you always want to be careful. And finally, if this was an active vote, if it was not a withdrawal, then we introduce this into the storage. And at the end, we will check the result again. So let's go to check result first. So we verify. So when check result is called, we check that the result is not sum. That's another way of checking it. And it also invariant. And we see what's the total validator stake. This is another method that is returned from context. And let's say it's saying we have 100 million total stake. And then internally, this is active stake. It means all validators who voted on this. And we're saying if active stake is more than 2/3 rounded down of total stake, then we reach the result. And that's pretty much over of this contract. So voting has completed. So this is fairly simple method. And we probably want to go to pink. So pink, this happens if on a boundary of epochs. So after an epoch switches, it means the new set of validators became active. Within the epoch on your protocol, validators do not change. So even if someone kicked out, they will be only inactive on the next epoch. So what we do, we verify that we didn't reach the result. Then we take the current epoch height, it's just an integer that always increasing, and we verify that it doesn't match the previous epoch height. So we started with epoch height 0, but every time a ping is called, it is it can update the epoch. So if epoch has switched, so it can pass 1 epoch or 5 epochs, doesn't matter. What we're gonna do, we're gonna go through all previous active votes who voted for phase 2. We reset the total stake to 0, and this is a Rust way of taking all the data out of Hashmap and setting it to default. So basically, we got a copy of the map from internal structure, and now internal structure contains an empty Hashmap. It's a new thing that it was introduced in like recent Rust.
So that sets them all to false. So that sets all the same size of votes, but all of them are set to false.
No, it basically just empty Hashmap. So it calls Hashmap default, set it to this variable. So let's go here. It basically calls replace. Replace does swap. But a second argument to the replace is a default of Hashmap, which is empty map. So it gave us a data from our structure, and now this contract structure contains an empty map. And this is just so we can do in one go modify the current map or the new map based on the data from the old map. So we basically just need account IDs. We don't need to know what was the previous stake. So we check if someone was removed from the map, or like removed from the active validators. So we get their stake. If their stake is positive, we add them to the total stake, and we keep their vote. But if they were kicked out, they have to vote again. I don't think this happened during the phase 1. No one was kicked out really from the validating boards. Maybe someone was. I'm not familiar. Actually, I think, yeah, one validator was kicked out. And basically we update total stake by recomputing what's the new total stake. And then we store all the results back to our contract state. And at the end, we do two things. We check the result. So after an epoch has switched, if validators acquired more stake or the total stake decreased, then the result might happen already. And we remember at which epoch we did this. So next time someone calls pink or vote, we don't need to go through this if epoch hasn't switched. So that's pretty much the voting contract. Basically, every time someone calls a vote, we first update data from the previous validators and write it into internal structure. Most important, we get the total voted stake updated, and then we call check result twice occasionally within the one call. And what's important is, even so we we can call ping here from one method, but also we can call ping directly by a transaction. So you don't need to revote, you can just call ping. So it's pretty much a contract. And the way Rust works, so there's a bunch of view calls. So one of them just returns a result. Another one of them is returns how much stakes it go. And the final is a functional way of returning all the votes. It basically iterates on the map and then wraps it into a specific type of the balance using into. So we're almost out of time, but I want to point out that there's also a unit test in the same code, and this is just a Rust way of doing this. And unit test can validate some logic within a contract by faking the context and stuff like this. Okay. Any questions to follow up before we close?
This is great.
All right, so let's go back to the call. Okay.
Thank you very much.
Thanks, everyone.
Yeah.
All right, let me stop.